Hey everyone, well here it is, the first episode on the cluster. I'm going to show you kind of what the cluster is, how it works, a little bit of how it works. We'll do a high level overview because I don't imagine too many of you will be trying to attempt your own repairs. But we will get into that, and from there I'll show you how to upgrade it. However, I would highly recommend sending it off to someone like Bob the cluster guy who does this all the time. But I will show you a little bit on what's there just for internet's sake. I know Scott Taylor used to do a lot of repairs as well, and unfortunately had a stroke and is unable to do so. So I think right now Bob is the only guy out there that can do this, and for the sake of continuing to keep the Ford Thinks on the road, I think it's really important to go over this a little bit and show how the cluster works and how some things can be upgraded to continue or make sure that it continues to work. So you undo the screws. There will be 4 screws that hold the LCD display in, that's on these smaller posts that don't have the inserts. And then there will be 2 screws that hold the main board in. So this is what it looks like, but really it's this side that you want to look at. So this is considered our J7A connector, and this is J8. So right off the bat, the first thing is high voltage comes in on this connector, and this is low voltage, 12 volts that comes from the DC-DC converter. This connector solely is for things like your headlights, your turn signals, things like that. This one has nothing to do with getting the cart to run. So we're going to start with this guy down here, and then we'll make our way around the board. So the first thing I want to go over is really what this board does. It does a ton, and I can't for the life of me figure out if the people who designed this board were really smart or were way in over their heads. And as we get further into this, if you have any background in electronics, you'll start to see what I mean by that. There's just a lot of wacky things. And what I think happened, and this is all me guessing, but what I believe happened was a lot of components were pulled directly from the shelf for the Think. And with that, it kind of came down to something that needed to meld all those things together. And I believe the cluster was that thing. So the controller that is near the motor in the back of the cart was a unit from GE. It's very similar to the ones in the earlier gym carts. So that was kind of off the shelf. They pulled lights and things from other other products in the Ford process. DC converter was off the shelf from Sevcon. There were a bunch of stuff like that. And so again, I think all of that got put into the schematics, and then at the end they said, oh man, we have all these different voltages and all these different things we need to do. How can we accomplish this? And that's what happened. So essentially, from a very high level, what happens here, this side of the board is low voltage, meaning around 12 volts and lower. And this side of the board down here is high voltage. It's actually some of it is running at 72 volts, and then it gets stepped down to 12 volts, stepped down further to 5 volts for things like this microcontroller. So what happens, voltage comes in right here on pin 1. And then pin 14, so 10, 11, 12, 13, 14. So this is ground, and this pin right here is power. So what happens, you can kind of see one of the common failure points is that the trace right here that goes under this resistor isn't thick enough. And over time, it actually, because of heat, will fracture and break. And so that's actually a good failure. There's not a whole lot you have to do there except solder a bigger connection on there. So I have this hooked up now. I added the key switch, and I have a little 72 volt converter. So really all we have to do to turn the cluster on is power goes to pin 1 and ground goes to pin 14. So this is 10 over here, 11, 12, 13, 14. And once you do that, then you will, if you have your screen on the front, make sure you don't touch anything. So I put a little spacer in between. With your key on, I have the key turned to the on position. You'll get, you should get an output on your cluster. Now the charge indicator will come on because it's actually pin 13. That is for charge indicator. And if you put if you put something right here on pin 13 and tie that to 72 volts negative, it will actually, or it should actually turn your charge indicator off. So that's something that is pretty easy to fix, and I'll actually show you. If you have your charge indicator on, just put something there, and then this is 72 volts negative. If you touch these together, flip this over. See, our plug is gone, and if I undo that connection, it comes back on. So for now, just to eliminate another wire that we're messing with, get rid of that. Okay, so a few things. I'm gonna try to put the board over here, kind of to the side, and put a multimeter so you can see what I'm doing at the same time. Well, that multimeter gave me issues, so let's try this one. All right, I'm not gonna say that I have this fully figured out, but I'm going to give you a quick walkthrough. So basically what happens, we have our power already established, we have our ground, we have the charge inhibit that's right next to that, which is pin 13. If you have any issues with that, it's the one right next to pin 14 right here. And you can tie that and pin 14 together to 72 volt negative, and that should make your plug icon go off and the charge, or the cart actually be able to go. If the plug icon is on and your cart is still able to go, there's an issue down here, but that's a little bit of a deeper dive. So let's start at the top. I have one of my probes connected directly to 72 volts negative because we're referencing everything from ground. So if we do that, we see our 72 volts coming in. All right. It goes through this, which is a power MOSFET. So basically, this is the on-off switch for the cluster in very simplified terms. It goes through an inductor, which helps, again, very simplified terms, kind of keep some of the peaks that you might see in voltage swings and sags to a minimum. And then it goes through some filtering capacitors, which are all these guys, and up to here. So what you'll see up here, you'll see our 72 volts coming in, and then the output is this side, and you'll see that it drops down to 54.5 volts. So that's the first one, and then it goes, this is called a linear regulator. So it takes a voltage and input, you give it a resistor value, and it will give you a lower output. So you're regulating the voltage down to a safer level. The issue with these is they can only regulate a percentage of the input. So in this case, we see about a 20 volt difference, which is right at the cusp of what these things are really able to do. And so what they did, which is not a great engineering practice, because it can lead, and it does lead, this is a reason that most of these fail, and fail pretty spectacularly. This can lead to a runaway event. If this guy failed closed, meaning that this input and this output directly connected because it got too hot over the last 20 years, then we're then feeding 72 volts into here and expecting an output that we're not going to get because it can't handle. And so this one blows, then this one blows, and that sends a voltage spike all through the rest of the system, which can have catastrophic impacts on other things. So basically how this works, when it should work, right? 72 volts in, 55 volts out, we have our 55 volts in to 31 volts, 31.75 volts out, 31.75 volts in to about 12 volts out. And this voltage over here, that 12 volts, is what powers most of the system. But you're going to see there's some other voltage regulators on the board as well. So an output on this guy is 5 volts. There's one over here that's 12.6 volts. There's one over here that's another 5 volts. And basically, all of these little guys that I just pulled out, all these linear voltage regulators, are just making various aspects of this board happy. All right, so we've talked about these three, how we take 72 volts, we're going down by about 20 volts, and again, to get us to about a 12 volt output. And then there are some other linear regulators on the board. So this one, for example, gets us down to 5 volts. This one over here, around 12 volts. This one up here, around 5 volts again. And then there's some other oddities. So like this guy right here is an isolated transformer. So it has an input side and windings in here. And then it also has an output side that basically mirrors the input voltage in this case. And so 5 volts is going in, but not connected. There's also a 5 volt output side. So that's it's completely isolated. So if there's a big voltage sag over here or voltage swing, that voltage will be mirrored, but if there's a spike, it won't be able to actually make it over to the micro. And that's a good thing. That helps to mitigate some issues getting all the way back to the controller. But I have seen a case where a voltage spike, it looks like, did make it to the controller and it failed. So the PIC 16 microchip controller up here runs on 5 volts. This is the serial transceiver. So this talks to the controller. And interestingly enough, it does not get the speed pulses from the controller. However, it does get battery voltage. It gets your motor temperature stuff. Your DTC codes, they come through this chip. The other thing that's really interesting, and again, this is more from an electrical engineering standpoint, that might not be of value to some of you out there, are these things. So these are opto-isolator circuits, or opto-isolators, as they're called. And basically what these do is allow you to run a signal without a direct connection. So basically what's in here, if you just think of it in very simple terms, there's a light and essentially a window with someone looking to see if the light's on or off. And if the light's on, then the person on the other side of the window continues and sends that signal through. If the light is off, then they don't send the signal through. So it's basically an indirect way of sending a signal. And it happens for most things that are coming out of this microcontroller. So one of those, being if it's in turf mode or if it's in drive mode or if it's in reverse mode, things like that come through here, and then make it back to various connectors on the bottom of the board. Something else that's interesting, this over here is a little power driver circuit. This actually solely powers the reverse lights. So if you have reverse lights that are staying on constantly, there is a good chance that if you replace this chip down here, that will fix your problem. It's just failed closed, basically. There's some other stuff going on. This is the crystal oscillator for the chip, so this keeps it basically in time. And then down here we have some other interesting stuff. So this guy actually helps with what am I trying to say? This actually, when you hear your relay click like every 30 seconds or so, it's looking for isolation between the 72 volt rail of the cart and the 12 volt rail of the cart. And if that fails, you're going to get an icon on your cart showing that there is a leaking voltage. And that is through one of these op amps down here. And if you remove that, you won't get the symbol on your dash, but you know, it might not be good to remove that. But you can. And then all of these other little things, they're all parts of very intricate circuits that are way more involved than they should be. So for example, a lot of the stuff down here, especially these, Q8 is one of them that's a bad culprit. I've had to replace Q16. These are all little transistors that basically turn things on and off. For example, if the plug icon is on your screen, it might be the case that you have to, let's see. It's likely that one of these transistors could have failed open or closed, and that will keep the battery icon from showing. It could keep the contactor from closing in certain instances. It could mean that the plug indicator on the screen doesn't go off, even though the cart seems to function fine. And these get really hard to trace down because what's happening, there's some bilateral communication. And so something from this chip needs to send a signal. It has to go through one of the opto isolators. It comes through some various components. And then down here, it could trigger a transistor, which leads to one of these output connectors that goes back to the motor controller. So if you have one of those issues, it could be a pin all the way up on the microcontroller. It could be a opto isolator. It could be a transistor. In the cases that I've seen, it usually is a transistor. So there's a lot here. I could go into a lot more detail. I feel like this is probably way too extensive for a lot of you. This is me trying to decode certain aspects of the controller, figuring out the state machine on the opto isolators, on what has to be on and off in order for it to be in turf mode, drive mode, off, and reverse. You know, you draw out all these circuits and see what's going where and why. And again, I really think that the cluster people doing it, I don't know what they were thinking. There's stuff on here you can just remove and it doesn't seem to affect things at all. And in the case of a repaired cluster, that really seems to be the case. So I'm going to move this guy out of the way and then bring this cluster in. And this one over here is one that I've done repairs on. So the first thing that you'll notice, maybe, there's probably several things you notice. The first thing that you notice, though, we don't have our inductor. We don't have our power MOSFET. We're missing a diode here and a resistor. We've taken out some of the capacitors. And more importantly, we're not reliant on these cascading linear regulators that can fail. So what we have instead of doing all of that power on the board, the better solution is to remove that from the board. So you don't have all of this stuff that's getting you from 72 volts down to 12 volts. You have a real DC-DC converter that has a lot of intricate components in here that does that for you. And what I've done, and what Bob and Scott have also done, so this is some of their work, is taken those components off the board. And basically you convert the input, which this has a very wide input voltage because you want that. Some people are doing conversions to lithium, so you're seeing more than 72 volts. If you have voltage spikes, you want to make sure that's considered. And then we're outputting the 12 volts DC that this wants. So basically, we have our 72 volt side that goes to the input on here. And then we have our 12 volt side, which comes from the output. And what that allows you to do is bypass a whole swath of issues associated with the power on this board. And then the other things that you're going to want to look into are your capacitors. So sometimes you'll see the tops might be a little bulged out. I would tell you to replace all the caps on the board, which is what I've done here. And depending on the version of the board, you might see a tiny little capacitor here, or like this one, you might see a big capacitor. Just seems to be a variant in the board. This one gives a pretty good example for a component that had blown up. This was Q23, and I'll have to find the video for exactly what that inhibited, but I believe that I can't remember. I'll have to look at what that is, and I'll put some clips in here for that. This one also had one of the linear regulators blow up, and you can see that it pulled up a little piece of the trace on the board, so we had to go in and fix that. This is the chip I was talking about for the rear backlight. And then here's some components that just aren't needed. So these are op amps that are used for voltage comparison. Same here, bigger version, same down here. This is the one that actually, I believe, showcases the voltage leak indicator icon on the card itself. This one, and if some of these are faulty or voltages are out of swing, best thing to do is remove those. Same for this guy down here. So that is basically cart operational side of things, which is this lower part of the board. But this upper part of the board, there's some stuff with the 12 volt connector that allow your lights and your horn and things like that to work. So basically what happens on this side of the board is that when you turn the key on down here, which is this connector, it's called J5. When you do that, a signal gets sent back up through these opto isolators. It tells the microcontroller, and then some things happen on these pins on the low voltage side. So for example, one of them is when you're in reverse, a signal is sent to this single pin right here that basically flips a switch inside of here and allows power to flow back through, directly powering the backup lights from one of these pins. Another one is there is a relay, a 12 volt relay under the hood of the car, and when you turn the key on in any position, it should pull that relay. It's connected to the ground side of that relay, and that gets pulled closed, and that relay then allows the DC-DC converter to be connected to your 12 volt system, and that's when you're able to use your headlights, your tail lights. There's some things that you don't have to have the key on for, but for the ones that you do have to have the key on for, headlights, turn signals, things like that, that flows through that relay. The other thing that's really weird, the turn indicators are directly on this board, and if you find them weak or not working, maybe they've burnt out over time, maybe you've lost a connection. I have one where the connection had just completely rusted through. You can replace these with just a standard LED, and make them whatever color you want to. Just, desolder them from the rear right here, pull them out, and then of course make sure that you have them in the right orientation. LEDs only work one way, and put them back in. So that's basically that. The other thing, I think these things are entirely too loud. When I open one of these up, I usually put a piece of tape, just electrical tape across this. You still get the backup indicator, but it's not nearly as loud as usual. And there's some other things that we could go into, but I think the next part of what I want to talk about here is this little board that I've made that is a substitute for getting the cart to run. and it's not much bigger than the than the high voltage connector itself. The way that I'm approaching this is these boards are never going to be manufactured again. I could send this off for several $100s, if not a few $1,000s, and get someone to do a full reverse engineering on this. That is a destructive process, meaning that they will take one of these boards that is functioning. They will take all the components off of it. They will sand away the top layer and then the bottom layer. And this has layers in between that they would then have to, what they call buzz out, which means that they use their probes and they have to literally follow trace by trace. So like you see this trace here, and you see that it connects here, and they would make sure that that beeps. And they would have to do that for every single trace that wasn't visibly apparent on the board. This is a better example because I have a clear what's called solder mask on here. But basically, they would do that. And then it's a very risky process because if that all goes well, then they have to go through and just make sure they can still source all of these components, which I have sourced most of these to repair some of the boards that I had. But then you have to go through the process of making a new PCB, testing it in the field, flashing. The biggest part is flashing the same code on this microcontroller, which I was able to extract. And I might, if someone knows a little bit more about a microchip PIC 16 controller, I might get your help to reflash that, because I have some new ones, and I want to see if I can do that. So all of that to say, I think that would have been an incredibly risky route to go down, to try to duplicate the controller. The other thing, the cluster. The other thing is that the screens aren't made anymore. I happened to find some new ones that still have plastic on them, but you're not going to find these anymore. So say I spent $2,000 to get a new set of these made. Well, that's all fine and dandy, but then we don't have the screen. That is a US custom thing that I've reached out to them and they've confirmed they don't have this stuff to make anymore. Then we're still dead in the water. So basically, with all that being said, the best course of action in my mind was to go in an entirely new route. The problem with that is that's also an extremely heavy lift, and you get past my knowledge of electrical components into the knowledge of software, and that's where things start to break down for me. So I've made this little guy. I have one that I've populated and it works. I have a version 2 coming in this week. All that this does, this is a phase 1 to get a cart going. If you have a cart that isn't running and you suspect it's the cluster or some other little nuanced thing, this bypasses safety features like the charge inhibit line. You plug in the connector, you turn the key on, and this gives you reverse, turf, and drive. You get your reverse buzzer, and that's about it. This will get your cart going. It doesn't do anything with the lights. It doesn't do anything with speed. This is solely to be used to get a cart running, and those things you can do with a different connector, or a different harness, or wire them up in a different way. But this is a quick and dirty, cheap method. If you don't have or can't repair, can't pay the cost to fix a cluster, this is the way to go. This is the first way to go. The second thought, or the next step in this iteration, if this is working well, is to incorporate this connector. So the next phase of this, again, I won't deal with a screen or a user interface or anything like that. It would be basically a bigger version of this that would have the 72 volt connector and the 12 volt connector. And in that case, you would gain your operations back for your turn signals and your headlights and things like that. that's really where I want to get, because I think that restores 95% of what the cart can do. And then, give me 2 seconds, without having to do a lot more work that I don't know how beneficial it will really be to people, we could just take the new model of this, put it in, make a 3D printed version of this that fits in the current holder in the cart, and then you could get something like this little guy, which is a GPS speedometer, and this could become the new display. So there's no use reinventing the wheel if there's already things out there that I could just incorporate. So that's kind of the thought process for now. I also had a version, this is a really pretty one, but this would be expensive. This is a full color touch LCD IPS panel. So this one is really pretty. This would be kind of like the cream of the crop if I did make a replacement cluster. But I think that where I've seen people in the age of Ford thinks is kind of trying to get them back on the road as cheaply as possible, just to make sure that everything works. And so this is probably a $250 plus option if I could even get it going. These boards I'm hoping to sell for between $50 and probably $100. And so that's really seems what the sweet spot is going to be. So all of that to say, 3 phases. This is phase 1, quick and dirty method, gets you reverse turf and drive back. Phase 2 would be making sure you can get your headlights and your turn signals back, some of your 12 volt stuff. And then phase 2.5 would be incorporating an existing display like this guy for speed, which I think is 95% of what people want. Most of the odometers are exempt anyway, and these things have a bug where they'll reset themselves to 0 randomly around 800 miles. And then if I really want to put the time and effort into it, this would be the ultimate solution, to have a replacement screen with a fully built out user interface that gives you, more information than you would ever need. But I don't know that I have the time with a full-time job to build this out. And I don't know that there's enough carts on the road that this really makes a lot of sense. There's really not a whole lot that would be added that this little guy can't do. So basically that's where we're at. I figured there's going to be a lot of questions on the cluster. And so what I really wanted to do was give an overview. I'm going to turn this off so that I don't actually accidentally short something out. What I really wanted to do was give an overview and then allow y'all to ask questions. Because the cluster, I could do 10 videos on this and we could go through each circuit, but I don't think that's really what's going to help people. I think that a lot of people that have carts out there are people with common knowledge. I think the people that understand the true electrical nuances of the Ford Think are very, very slim at this point and getting slimmer. And so I just want to get a video out there that kind of shows what the board is, how it works, how you can replace some components to get it going. Put some documents up that people can download if they want to do repairs and they have electronics experience. If you've never soldered before, do not touch one of these boards. They are incredibly hard to find where they haven't just been mutilated. Please do not mess them up any worse. Reach out to someone like Bob, the cluster guy, who has experience fixing these, or buy a bypass. And I'll continue working on those, and we'll continue to update as I get more samples in. But hopefully this gives you a good first indicator of the complexities of the cluster, and yeah, fun stuff. All right, so this is more for my own sanity, but to also kind of show what's going on these Ford Think clusters. Alexa, stop. So this is more for my sake, but hopefully it helps some of you as well. So where this all started, I had what was known as an MMC cluster from Scott Taylor at Electrons in Motion out in California. He used to do a lot of work on these clusters, and kind of had already led the torch and or was carrying the torch and was the first to really figure out how to make these live longer. With that being said, some of these things were already removed from the board. So this guy over here, these two components, this guy down here, and this one. This one I know is an op amp, I believe, that controlled the leakage sensor or components on the board. So that would test and put an indicator on the LCD screen if it detected leakage of current between the 12 volt rail and the 72 volt rail. I assume that over time that op amp fails, it gets too sensitive and probably keeps that light on. Some other things to note. So pin 13 down here is charge inhibit. It directly goes to Q16, and if that transistor right there is busted, you will not get contactor closed and the cart will not run. So that's the Q16 right there. And all of these that seem to be problematic have a code of H02 on the top of them, or H02. So Q16 controls the actual contactor circuit. Q6, which is this one right here, controls the plug indicator on the LCD screen. So you can replace this if you have if your contactor is not closing and your plug indicator is on. You can replace this and the contactor might close, but you might still have a plug indicator on the screen, or vice versa. So those are two independent circuits. This guy goes up here to an opto isolator. I believe it's this one. It might be this one of these. And actually turns this on, which sends the signal to the microcontroller, the PIC up here, to turn on or off the plug indication on the LCD display. This guy over here is a MOSFET, a driver for the reverse lights. I actually had one of these blown up on a board. It looked like moisture came in and shorted it out. So this is actually the gate, the switch to this, and then one side of this is your inputs. They're all tied together, these three, and these are your outputs, I believe, all four of them. And the reverse lights get their power from the 12 volt DC-DC converter on the unit. The other things to note, we'll go through the power, how the power works on the board here in just a second. But other things to note, so there is a relay on the cart itself that gets its ground from a connection on here, and it is pulled down when the key is turned on, and it actually deals with Q23. It goes through this opto isolator and also deals with Q22. So those components right there, if you have a problem where your 12 volt DC-DC relay isn't firing, and so you're not seeing a backlight at all, or you're not seeing any lights, reverse lights or headlights, turn signals, it's probably something with Q23, this opto, or Q22. Some other things to note, let's go into power real quick. So power comes in 72 volts. Historically, how it worked on the board it went through a big MOSFET right here. I think there was an inductor type thing here. And then it actually filtered down through these. So this would step it from 72 to like 50 volts. This would take it to 30. This would take it down to like 14. And obviously this is a huge heat cycle. So these were being ran at like their top, at the top of their limits, so to speak. And so you can imagine with charging, discharging, heat cycles, being outside, when these go, they typically all go, or one fails, and if it fails closed, then you've created way too big of a differential for the next one, and it fails immediately, and then the next one, so forth. So that is important to get rid of those. And so what happens here with these connectors, this is an isolated power supply that takes in 43 to 160 volts and then outputs 12 volts. There is a little resistor here. This bumps it up to about 13.3 volts. And that is what is doing the conversion now. So it happens off the board, makes it a lot safer for everything to occur. So once it's stepped down to that 13.3 over here, this steps it down. I believe it's this one. Steps it down to 12, and then it gets stepped down to 5. And this is actually a isolated transformer where it takes the input from the 72 volt side, and then it's isolated from the 5 volt side, which goes up here to the PIC and powers the microcontroller. Those are the things I think that I've learned so far. There's some other little nuances, but those seem to be the most common failure points. So that is where I am right now. I will continue learning about these guys, but hopefully that gives you a little bit of an indication of how this works from a top level. I have made some schematics. I have this sheet for kind of the top of the board. Also have this one and some other ones with some logic tables of what optos turn on when the switches change from off to reverse to turf to drive. But right now I feel like I have a pretty good grasp of overall how this works. There's a few more things I want to check on each board, like battery indicator level. Some of those seem for some reason to get stuck, even though it seems to get battery indicator level from the motor controller as well as speed from the motor controller. I actually have a cart right now where speed is not working, and I believe it's this is a serial transceiver chip, but I believe the chip on the in the motor controller itself is bad, and it's not getting a speed signal because the board I'm testing with in another cart seems to work just fine. So yeah, that's where we're at. Here's one more we're gonna try to fix. So this one has a plug indicator on, but besides that it seems to work. So we're gonna replace Q6, which seems to be the main culprit on the plug indicator. Again, Q6 plug indicator, and Q16 is the actual contactor commander. So I know this one zoomed out a little bit more, but again, Q6 is this one down here. Got me some more HO2 transistors, which the actual name for these are let's see here, DTC 323s. Some of that other stuff past there is just how it's actually packaged. But let's pull one of these things out. Something inside of these seem to not be too happy with the Ford Think. Of course, it is a pretty demanding job for these little guys. The loads in a electric vehicle, you got current sags, voltage drops, all that kind of stuff that probably doesn't treat these components very well. Of course, this board looks like it was rushed to manufacturing, doing a 72 volt down to 5 volts essentially on a PCB, which it's kind of ingenious how they did some of this, but some of it is just like way more complicated than it needs to be. It would help if I would turn my heat gun up to something that will actually melt solder. Let's give that just a second. I was wondering why that wasn't working. Should be. There we go. All right, so that's a bad component potentially. Let's flip this little guy over if I can without burning this board up. You gotta love these things sometimes. They're so. This one's not even that small. Oh my gosh, I think because I'm on filming this that it's gonna take 3 times as long. All right, there we go. So let's pick this guy up from the sides and get him heated back up. Oh, shit. I'm blowing things all over the place and I don't even have the air turned up that high. Let's try that one more time. Right, because this connector is right in front of it. I have to grab this a little bit of a different way. I really like trying to get these looking decent, but it's hard sometimes. All right, that seems to be on there. And then I always like to press down from the top on these if at all possible and kind of heat them up one more time just to make sure that they're pressed all the way down against the pad. So you can see HO2 down there. Looks decent. So let's throw this back in a case. Do this in here. So very simple. It has a broken post and a bad looking connector on the back. You know, but some of these things have been worked on several times before. I've seen them, this being one. Looks like someone else made a trace repair. I've never seen an issue with that trace before, so I don't know. There's no telling what happened there. If someone's pulled up a trace when they were doing something else or what, but this one looks like it was just handled roughly all over. All right, so we have that in. We'll set a screen on it real quick and let's go see what happens. So I actually just discovered a mistake that I made. I believe that I made. I heated this chip up because I seem to have a grounding problem. And by doing that, it looks like I've bridged a connection. As I look like a total amateur right now. There's way too much solder on here. So My little solder sucker. We're waiting on my heat gun to warm up. And we're actually going to pull this chip off real quick. I think that these three pads on this corner are actually touching, or either the chip has gone bad internally. But we have continuity mode on. If you touch these three all beep together. And if I bring in another test board, there's another one. You touch these three. They do not beep. So, anyway, I've been debugging while this plug indicator is on, and I think this is the reason. So, I'm gonna heat this chip up really quickly and see if we can get it off of here. I don't really have the right chip or tip for this. So I have tools split between here and the garage where I'm actually taking the carts apart, so it's a little bit of a pain. Getting close. Looks like there could be a little wire actually that is bridging those. So this is the corner we're working with, and everything here looks good. I'm going to heat this up. But if you look really closely, it's kind of hard to tell. Let's see if I can. It's a tiny, tiny little fragment right there. Potentially, that could have been the silk screen under there. All right, so now what we're gonna do, we'll just make this really easy. I'm gonna test. So those are not electrically connected, which they shouldn't be. So now let's test this chip. It could be that this chip has been donezo. Just do it like this. Test these pieces here. If I can get it held in place, which I might not be able to do. See if I can get a clip. So the chip was like this. We're just gonna test these. That's me touching the same pin. They seem fine. So There could have been a tiny little solder blob down there. I'm gonna clean these up just a hair. I don't fully understand, but hopefully this solves it. So we're gonna heat these pads up again. Before we put the chip down. Try to hold that in place. It is not happy. I'll get it right where I want it. And we'll heat it up. I feel like that's pretty heated. I can't even see what I'm doing. Alright, I'm gonna let that sit for just a second. And then what we're actually gonna do is test this again. So we're still in continuity. Let's check these three. That's me touching together. Okay, that's promising. So now from this guy, U14, this one goes to ground. This one goes to one of these. That middle one. Okay, I think that's gonna solve our plug indicator problem on this one. Let's let it cool off just a little bit. Plug power in. Let's turn it over. Yay! Plug icon is gone. It's just me shortening something out, but all right, plug icon's gone, and then if I unplug this, it's back. All right, sweet, fixed. That was a fun one. All right, quick little video. I just want to show y'all what a bad solder joint looks like. So this screen, you can see it's fully lit, but if I press right here where the chip is, you can hear it click. That's me just pressing down with different force. And if I do that, I had it just a second ago where the screen actually turned off completely. I'm gonna unplug it with my finger on there and plug it back in. See, so what we're seeing is it looks like a bad ground or a pin on the microcontroller isn't connected. So if I let off of this micro, we get everything on the screen. And if I turn it over, where I was pressing was right here. So when I put this back on last time, it looks like there's a cold solder joint that didn't fully connect. So we're gonna re-solder that guy one more time, heat it up, make sure everything seems like it's touching, and go from there. So sure enough, I'll try to show y'all this through my microscope here. Putting the camera up to the lens. This is after I've soldered it. It's really hard to get focused. But you can see those pins. Everything looks very clean on that side. Can look on this side as well. Everything looks good there. Do it from the bottom. It's kind of hard to get to the top, but everything's also clean there. So we'll give this a test out tomorrow, and should be good to go. One more thing I want to show tonight. This is the Ford Think Cluster LCD screen. This one's in pretty rough shape, so doing a little experimentation on it. I actually have what's called a backlight strip tester. You can find these on Amazon. Basically what it does is it will ramp up the voltage to turn a backlight on without blowing it up. And what you can do is take these leads. K is your negative connection and A is your positive. And when you connect these, you'll get an output on this screen here. So about 9.3 volts DC. And I don't know that I'm going to be able to show you this. But if you do that, let's see if I can find an alligator clip to put on here for these. One second. So this K, you can just follow the trace. It goes to this pin right here. Push the sleeve down so it's not touching the other pin. And then A is this bottom one. This thing will shock the crap out of you, so you gotta be careful. But you can see when I do that, you can see the backlight gradually comes on. See, when you hold it there, it gradually comes on. So this is me touching it. Backlight gradually lights up. And around 9.3 volts. Now the other thing is, if we zoom in here, this R5 resistor looks awful, and R6 also doesn't look the greatest. So we know the backlight works, so that's good. I'm gonna unplug this thing because, like I said, it is capable of putting out some pretty serious voltage. And I've gotten shocked before, and I do not want to get shocked again. So now what we're gonna do, we'll just use a normal multimeter here. So we'll put it in continuity mode. And what we're going to do is test across R5 and R6. I bet one of these is bad. And we're not getting a beat. So R5 is bad. R6 seems to be bad. Oh, I'm an idiot. Now, this isn't gonna just show we need to be in resistance mode. Because if these likely won't fail short, these will likely fail open, which it looks like that's burnt right there. So we're showing no connection, no connection. I'll zoom out so maybe you can see this as well. So no connection on either of these. So those have probably burnt up. And then on this one, 472, so 4.7K, which is exactly what that one's reading. This one's 103, which would be 10K. That was 2.242, so this would be 2.4K, which is right. 1 meg, 105, and 184, which is going to be, yeah, 1, or maybe that's 104, 184. So anyway, close enough. So those all look good. Then if we check not continuity, capacitance, we should see, so 10 nanofarad, which is pretty standard. Let's check this one. That one seems to be kind of jumping around. I'm not a huge fan of that. Let me swap these leads just to be... Maybe I'm not holding it on there long enough. 1 second. Hmm. 0.27 nanofarad is what it's showing. But there could be a drain or something somewhere. So anyway, these are bad. 330. Is what the marking shows. So we're gonna replace those and see what happens.